Good afternoon, everyone. My name is Laura Precupanu. I'm the SP Regional Director for Europe, organizer of this edition of the SP Europe Energy Geo Hackathon, and today I will be the one moderating this session. My suggestion is to wait 1 more minute because I see people are still joining the call. And then we will start with the brief introduction of our speaker and with today's session. Thank you very much. I think we can start. Is 2 minutes past the top of the hour. So good afternoon to the ones who joined us a bit later. Please allow me to share my screen and to show you where we are in terms of our bootcamp schedule. So we are with the bootcamp number 4. Machine learning methods is the first bootcamp on this topic. We will have another one later in the schedule. And for today, we have with us, and thank you for joining us, Mateusz Zareba. He is a very experienced professional working for Halliburton here in Europe. Mateusz holds a PhD in Earth Science from AGH University of Science and Technology in Poland, and his expertise spans geophysics, seismic data processing, and data-driven solution. He received the Geologist of the Year award in 2019 from the Polish Ministry of Environment for proposing a new seismic signal processing technology to the map of Tatra Mountains crystalline core. Currently, he is a G&G and data science technical sales consultant for Halliburton in Europe, building on previous roles as on-site Halliburton consultant for Shell and positions at GK Processing and Geophysica Toru. Mateusz, thank you very much for your time. I know you travel a lot. I know you are pretty busy, so thank you for accepting our invitation. And without any further ado, the floor is yours. Thank you very much.
Thank you, Laura. Welcome, everyone. Yeah, I'm welcome everyone from Aberdeen, but in general, I'm based in Krakow, Poland, where we've got an office. Today, I will show you the introduction to machine learning, but I will also show you the introduction for those who are not very familiar with seismic data. What are the seismic data and how to deal with them in Python? And if there will be enough time, I will try to show you what I've done for my PhD, as it was a complete study that was involving signal processing, statistical analysis, and also a machine learning part. And this is the short intro. I don't know what's your background or expertise field. So some part may be boring for those who are geophysicists or geologists. Some part may be boring for those who are a data scientist. But in general, it should be like a complete story from the beginning to the end. Yeah, and I was trying to prepare that presentation for you today from very basic going through more advanced techniques. And if anything will be not clear or you would like to ask a question, so just ask a question. You can interrupt me at any time. Okay, so let me share. Okay, now you should see my browser, yeah?
Yeah, we can see your screen.
Okay, so I'm a geophysicist by the background. So I was studying on my engineer and master degree, the applied geophysics in Krakow. And then I continue my learning and doing the PhD in the border between the geophysics and data science. And it consists of two parts: creating a software to calculate an important feature, and then to make a data science case study on that. But for today's for this hackathon, we will be using you will be using geophysical data, seismic data, and probably well data as well. For those who are not very familiar with the methods, so the geophysical methods are based on the physical properties of the subsurface. And of course, the subsurface consists of different geological medium, different geological complexes that may have different and obviously have a different properties. And based on the different physical field, we can get a different information. And here I put you a basic introduction to the geophysical methods. So seismic methods that we can divide on reflection and refraction methods, and mostly for deep seismic, for exploration seismic, for geothermal exploration, you will be using reflection seismic, and the refraction one will be used only to calculate the static correction and to get rid of the near surface zone effect for your data. Then we've got another one, which is a borehole geophysics and well logging. Those methods are very advanced. Are in the well, you can measure all the physical fields in very high resolution. So more or less they consist of all other methods. So they can use like seismic waves, acoustic waves, electric field, and gravity method, and many more. Then we can use also, in case of the exploration, electrical method, which can consist on resistivity and induce polarization, and gravity methods, where we will be analyzing the component of the gravity field, magnetometry as well. And for the new surface zone, for the engineering application, GPR is very popular, and now we are gaining more attention in the geophysical world to the satellite-based remote sensing techniques. Yeah, and I will focus in my presentation and in my example for you on those two, so on seismic methods and borehole geophysics. So practical part will be for borehole geophysics later on, in case of the data science. The presentation from my PhD will be about the seismic methods, and the practical part will be how to deal with the seismic data. But to give you a little bit background story why the seismic data are very wide used. In the basic ray tracing approach, we can use the theory that will be consisting on reflection, refraction points, and then we will be assuming that the seismic wave is traveling through the ray path. Like you can see here, this is a very schematic picture that I've done. So there you cannot count that those angles are correct, but the general introduction is that we will be finding in seismic methods the common points from where we've got the reflection from the border where the two layers are different in case of elastic parameters. And therefore, if we will be going farther from the source, which is here a star, with the receiver, then we will be able to observe the deeper layer, as you can see here. This is the basic theory. We also use in the seismic the wave theory propagation, which better describe the seismic wave propagation in geological medium. And we are using a wave equation for that. Here you can see the acoustic wave equation, which can be used for modeling for many procedures that we are doing. But of course, we need to remember that this is the acoustic wave equation. So the equation that was prepared for the acoustic wave propagating to the air. The geological medium probably is described with a different equation, but this can give us the information about this approach with this acoustic wave equation approach about the geological medium with enough accuracy to make a prediction. And here you can see a sample of the software that my advisor was preparing for the modeling. So how the acoustic wave is propagating. And now let's move on. Why we can observe the reflection from the different layers in the subsurface. Here you've got two parameters that are very important in seismic. So the first one is a velocity and the second one is a density. Combination of those two, as you can see here, will give us the acoustic impedance. Based on that, we can calculate the reflection coefficient. So here you've got the equation. You don't need to remember that, but just to give you the overview. Of course, we can observe the refracted waves only when there is a difference between those parameters. So if the combination of those two is different, so therefore we will be able to see it using a seismic methods. And we can divide the seismic methods on 2D seismic and 3D seismic. Of course, we are also using right now a 4D seismic, but for those data science case study, let's focus on those two, which are related to the acquisition geometry. In 2D seismic, we will be observing and we will be shooting and propagating the wave from the source, where the receivers will be on the line, more or less. Sometimes it can be a little bit deviated, but let's assume that it's on the line. And therefore, when we'll be moving with the source here, we can then create a geometry on the profile that will give us, after a lot of processing, the seismic image of the subsurface. So here you've got the example of acquisition. So those are receivers. And here you can see a source. And let's assume that we are creating a wave and all the receivers are listening and recording what have been reflected or reflected. Then we are moving with the source. And now we will be observing a different wave path. Then we are moving another time and another time and another time. After going to the whole line like that, we can then, after the processing, get the stacked image of the seismic, which you will be probably using later on. And how the 2D seismic shot gather looks like. So here you can see the 2D seismic shot gather. And what you can see here, each line is a seismic trace. So the receiver, we can assume this is a receiver, and the shot point, so the star, is here. You can see the signal here. And of course, you can see the noise as well here or here. After the noising, that one, and after applying the kinematic correction and strengthen the reflections, and after sorting to the CDP domain, so the common depth point of domain, we will be able to see the stack. We've got a different way of observation, which is a 3D seismic, where we will be using an array of receivers, as you can see here. So we are adding a dimension. We are not doing the line observation anymore, but we will be had a grid, let's say, of the receivers, and then we will be moving between this grid with the source. Of course, it's not like that all of the receivers are listening, are recording at the same time. There is a special pattern that are taking just a part of these receivers, sometimes maybe all of them, but in general there are different patterns of acquisition. But just to get the overall feeling of what the 3D seismic is that we are using an array of the receivers, and we are changing the source of waves. And here you can see how looks 3D seismic press tag gather. So you were seeing in the previous example just one line, yeah, because we've got the 2D line, and here you've got the 3D, and from that array we can see many different gathers assigned to one shot point. And now we can have a few different steps in the seismic surveys where we can use data science, when we can use machine learning, when we can use the power of data to improve what we've already created. I'm very happy that we've got that hackathon, because obviously we are very advanced in the processing techniques, in the imaging techniques, in the interpretation techniques, the physics based. So when we are now transferring to the data-driven world, the machine learning can help us a lot, because in this domain, we are collecting a lot of data as well. But let's start from the beginning. First, there is a survey planning. So someone has to plan how the geometry will look like, what will be the spacing between the receivers, what will be the shot point moving step, and so on. And of course, when you are designing the seismic survey, you have to remember that you are designing that survey for the particular structure. So sometimes it won't be easy, for example, to connect two different 3D seismic, even if they are overlapping in the straightforward way, because of the design for a different subsurface structure. And then we've got seismic acquisition. So someone is going there to the field, putting the receivers, geophones typically, and then they are collecting the data. After that step, the data from the field before stacking are coming to the seismic processing department. And in the seismic processing department, you need to first assign the geometry, then remove the noise, then include the static correction for removing the influence of near surface zone and elevation. Then you need to analyze the velocity to give the kinematic correction to the data. Then you need to do another round of automatic static corrections and another round of velocity analysis, and then migration. And after then, many procedures, many QC steps, and of course, a lot of these techniques are human related. So you will be judging what is the outcome of that techniques. So it's always good to think about the data science as kind of and machine learning, those procedures, as another version that can help us reduce the uncertainty related to the human mistake that you can doing the seismic processing. And why I'm telling about this, because when I was doing, for example, the processing for the survey where there was over 30 lines, so I've got like the pre-assumption from the line to line, and you cannot be 100% sure if this is a good one or bad one, and therefore you are multiplying that human perception-based error. So this is a good place when you can also include machine learning data science techniques to reduce that uncertainties and to reduce that error related to the human perception and the human habits, because obviously when you are doing the processing, when you are doing the statistical analysis, the classical one, therefore you've got habits which not always can be a good one. And then once the data are processed, you can go and do the seismic interpretation. And we can say like a seismic processing is closer to the signal analysis, to the physics, closer to the software development. Then the seismic interpretation is much closer to the geology. So during the seismic interpretation, we will be using different techniques to interpret the subsurface from the seismic, and then to translate that one to make those data the information for the geologists. Because you have to remember that the seismic in general is acquired in time domain, and the geology is in depth, and the well is drilled in depth. Then therefore we need to be able to translate the signal into the information that can be used by the geologists, by the reservoir engineers, and by the decision makers at the end. So this is like the seismic, very basic way of proceeding. What can be the feature calculated from seismic data? Of course, each seismic processing software has the bunch of attributes that can be calculated. Some of them can be used as DHI, direct hydrocarbon indicators. Some of them can be used, for example, to see particular structures, or to see defaults, or to see the geometries of, let's say, for example, old rivers, or the structures that you want to see. But I put here some basic one. So we can have like amplitude attributes, and of course you can calculate maximum, mean, the change of the amplitude. Then we can also take a look on the frequency attributes, time domain attributes, about the energy, about the crossing rate, spectral attributes, and statistical attributes that can be very useful. For example, kurtosis can be used to make dephasing or zero phasing of the signal on the particular horizons. Texture attributes that I was related before to the particular structures, amplitude, frequency decompositions. In the processing, we are using a lot of different domains and a lot of different transforms to see the noise and the signal more clearly. Phase attribute, stratigraphic attribute, seismic attributes from machine learning. So for example, the PCA or waveform classification. The PCA techniques has been used in a seismic for a very, very long time, and it was well known already for the geophysical industry, as well as neural networks. So we have been using neural networks since ages for the first break picking. Depth-related attributes and structural attributes, but probably for calculating the features, you will be using libraries, or maybe you will be using a software. Of course, the best one is Decision Space Geosciences to calculate the attributes that Halliburton is providing. But in general, there are a bunch of attributes ready to calculate that can be your features and that you can use in that hackathon. But let's, oh, I've got like a typo here. How do we store seismic data? We are in general, the industry is storing the seismic data in segway format. Of course, when you will be importing the segway into the Python, you will be converting the segway to the structure that you need, let's say to the Panda data frame. But if you will be also importing the data into the third-party software that is designed to do the interpretation or calculations, of course, all of the software will be somehow transferring the segway file into their internal structure to speed up the calculations. But in general, we are saving the final data set in the segway format, which is standardized in the industry. And once you export something to segway format, then everyone probably will be able to import it to many different softwares. And also you will be able to import it to the Python. Segway format detailed specification can be found on SUG library. So if you will put in the search segway revision 2, for example, and then you will be prompted to the SUG, which is a Society of Exploration Geophysicists. You will be prompted to the detailed specification, what you can find in the segway format, on which byte positions, and so on. The segway in general consists of a header where you will have information about where there are stored information about the position of the traces, about the reference system, about the coordination, about the scalar values, and so on. We will be looking on them later on. Then you can also include a textual header where you can put the information that are written by finger. So for example, you can include the name, you can include the processing history to give the knowledge for the people who will be using it, who will be importing, what signal processing techniques has been done on that particular header. And then you've got the binary data. Where are your data? So where is the signal? Where is the sampled signal of what has been recorded by the geophones? Any questions so far? No, not too boring.
We do not have any questions in the chat box so far, Mateusz. And
okay, so I will show you two libraries to import segway files, to import 2D lines, and then to import the 3D line. So first one that I like is Segisag, because it's easy to have like an instant visualization of the data. But there is also other very popular, I think, done by Equinor, Segi.io library that is also wide used. So here I've got the library that I need to import to work with the data. Here is my line that I will be using. I'm using publicly available dataset to show you that one from the SMEHIA dataset that can be found on CO2 data store page. And there you can download that dataset for your own if you would like to. So here you've got example how the text header of this data, this seismic line looks like. So you can see when it was exported, then the name, the type, what you should expect from what is the number of the first trace, what is the number of the last, what was the shot point, which here in the stack data is not very needed. What are minimum and maximum of the coordinates, time, and what is important for you, you've got the trace header locations, because sometimes, of course, everything is standardized in that format, but you can write information in different on different bytes, and then you won't be able to download the data using the standard byte locations. So here always you can check, and when you will be loading your data set for this project, it's good to check on which byte you've got what kind of information. So here I can see that, for example, I've got the inline number here, the CDP number on that bytes, the coordinates. So all I need, I know where it is. And then using a scrape function, I can see the header. So here I've got the consequence traces, and then I can see the information assigned to each of trace. So I can see that I've got the first CDP 1993, which is correct because here it was 1993, and the last one should be 6738, and I've got 6738. It looks correct. In total, I've got 5,646 traces. When I will plot the scrape histogram, so you can simply use scrape.hist, I can see where I've got the data. So as you can see, there is a lot of locations of this header where I don't have any information, which is not needed for this data set. But sometimes you can see the distribution and QC the data here. Then I can do a scan of the header, scan of the data. And based on this, when I will use and reduce that number by those who has any values, yeah, because when I've got here only zeros, so the standard deviation will be 0, then I can filter data. And now you can see that I've got this information on this byte location 1, 2, 3, 4, 5, 6, 7, 8, 9, 9. And when I will go back here, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it looks correct. The same I can do with the scrape function. So when I will use that code, then I will be able to see only important columns in that segue, which has a value that are changing, which are not zeros. Because in the first option, I have the table with all the values. And now when I plot the histogram, I will be able to see exactly the data I have. It looks okay. And now, I will be loading the segue using a segue loader function where I can specify path, and I can specify, for example, CDP X and Y coordinates by its location. If those are standard locations, therefore you don't need to specify anything. But if you want, if you will have other, or you are unsure from analyzing the header here, and from analyzing those pictures, you will be able to correctly put the numbers here. And of course, you need to specify a vertical domain. Here I've got the time data. So I put here TWT, which is travel time, double travel time. And now is the time to plot the data. I need to transpose data to have this orientation, like a CDP on X, and then to have like a time on that axis. I will use seismic color map. And here you can see the line. with the amplitudes. So we can see that we've got the geology that is not flat, not cake base, but something is going on here. And now when I would like to see this loaded segue into V2D, then I will be able to see that I've got X-array dataset with the dimensions based on the CDP number and time. And then what are the coordinates? What are the variables? What is the sample rate? And other information which is useful. Here you can see the function that will allows me to see this spectrogram of the data set. Okay, which is the shape of spectrum is okay, but the frequency is not correct here. So don't take it as a good example. I didn't check that. But in general, the shape is okay, but we should expect much more lower frequencies for a seismic, let's say around 80 Hertz. Now, here you can see how to put the data into the data frame. I like to also do the re-indexing of the data to not have double indexes, as here you can see, because it will be double indexes by CDP and time. Exactly the one was the coordinates for X-array. And then I'm cutting the data set for data below 3 seconds. I don't want to see the data below the 3 seconds because, for example, I'm interested only in this area. So I can cut the data. So here is the data frame that you are getting from the loaded segue. Here is after the re-indexing, so you can see how many samples we've got in the whole line. And here you can see the data that are plotted from the data frame. Here I put a function, but of course you can find them. And don't focus on them too much for calculating some kind of the attributes like instantaneous phase. So they can be easy to write, but the code that I'm showing here is not like a 100% correct, but it's calculating the instantaneous phase. So don't use that code. I just put it here to show you what can be calculated with some mistakes that I intentionally put there. And here you can see the values. Then, for example, you can calculate the envelope, energy envelope based on that. And then you can calculate the semblance. And all of those parameters can be your features. So you have to first decide what representation of the signal, what dimension, and what domain that you would like to transform the data to will be the best to get the information from your data. And here I reindex and pivot the data frame to show you how we typically look on the data. So, for example, when I'm loading the data to our software, I'm always doing a QC like that. So I've got here the CDP numbers, which represent the traces. So exactly, this is one CDP, another, and another. And when we add all of them, or when we plot all of them together, then we will have a seismic image. And this is what you can see here. And you can see also that here we've got the time, and it's ending on 3 seconds because I cut the data like that. And here we've got the CDP, and exactly what you are seeing here is plotted here. So this is the plot of that, and those are the values in the tables from where we get those data set. And the same for the rest. Here, example from Segui.io, how to get the data. So it's a little bit different way of dealing with the data. First, you have to open the file, but it's specified in the documentation. Then you have to specify data, time, and CDP, from where to read them. And then, for example, you can see how to get the basic attributes. And going down, you can see the different representation of the data in the grayscale. You have to remember, and when this is some kind of the advice for you, I don't know what solution you would like to use, but remember that for the human eye, so if you want to use some techniques from computer vision, for human eye is extremely important what color are you using for the data to get more information. And for instance, you can see here that we've got the grayscale. And in the grayscale, we are able to better see some kind of the noise. We are able to better see some kind of the continuity and discontinuity into the data. But for example, in the color scale, therefore we can see some more information. We are able to see a little bit more about the amplitude changes itself that are not really related to the structure differences. So just for your attention, remember that the color bar and the color that you are using for making the seismic image, for making the seismic plot, for seeing the data matters a lot. And now we can move to the 3D seismic data. So again, we are going through the same thing. We will be scanning 3D segue from the same data set, from the same SMEHIA data set that I downloaded from CO2 data storage that you can also use. It's publicly available. And here you will be able to see that we will have a little bit more information, because beside the CDP, which in case of 2D was representing the next traces, we will have inline and crossline. And when the inline and crossline will cross, there you will have a particular CDP. I'm using a partial scan to not include all of the data from the 3D dataset, because a 3D dataset is typically much bigger than the 2D dataset because of the number of data. You can, it's not correct way of thinking, but you can imagine that the 3D is a set of the many 2Ds. Yeah, and let's go to the histograms. So here you can see how the histograms looks like for that, a little bit different than for 3D. And let's move to the text header once again. So we again can see similar information, but instead of the CDP, we've got like the first inline and last inline, and the first X line and last X line. So those are the information that are telling us about the geometry of the data itself. And therefore, of course, we've got like a binary header location, trace header location, which are important there when we don't have like a standard bytes location. And now again, I will be using segue loader, And I will be specifying here that the inline is starting from the byte number 5, the X line is starting from byte number 21, the CDP X, CDP Y, and the vertical domain is, again, it's a time domain. When I will take a look on data as X-array, now I will have more dimension, the 3 dimensions. Previously, I've got the CDP and time. Now I've got inline, X-line, and time. We can see sample rate. And now, when I want to plot the data set, here I need to specify the figure, and I will need to specify inline, X-line, and therefore I need to transpose them, and here I'm putting inline, which inline, so which part of the 3D data set I want to plot. And here you can see that for inline 1450, I plotted all X lines. And I've got like a seismic, seismic image of the structure here. But let's see how the X line will be looking. So now for the X line, which is in the perpendicular direction to the inlines, the data looks like that. And here, when I'm plotting particular X line, it will consist of traces represented by different inlines number. So this is how we plot the data set in 3D. And of course, you can see it in the cube when you are using interpretation software. And here you can see the geometry, so how the survey were looking like based on CDP-X and CDP-Y. So this is the basic of how to import the data and how to transfer the data. Not always is the best to go directly to data frame. Sometimes it's better to use the libraries that were designed for SegWi to QC the data, to see how data are distributed, to check what features will be the best to calculate. And of course, when you will have wells, you can also use that library for the, for example, to the arbitrary line through all the wells on your surveys and to see how the geology is changing based on the seismic image from well to well.
Mateusz, talking about libraries, we have a question in the chat box, and maybe it's better to address it now rather than later. Marin was asking us, which Python library do you recommend to work with SEGY if we consider the size of the data?
So I'm using mostly that one. So that SEGISAC, you've got here examples of the code. For example, how to plot the Presta gathers. So it's quite advanced.
Can you please drop the link in the chat box?
Yeah, I will drop the link. And also you can use SEGI.io library, which is also quite popular library. So it depends what you like, but for the plotting directly, I like this one. But the SEGI.io from Equinor is also a good one. So those two I will put later on the links to the one that I was showing here. And what I remember here, you've got also a video with the tutorial. So if you, for example, we need more explanation, you can also, go to the YouTube channel and check it. And yeah, it's very easy to use. And I was using a lot of softwares, and this is designed the way that I'm thinking. So yeah, it's a good one.
Now that we interrupted you, basically, We have one more question, which was addressed by Luca 5 minutes ago. So I think it's very well connected with what you presented in the last minutes. And Luca is asking how you define and treat outliers in seismic data attributes.
This is not very straightforward answer for that, because it depends on what is the input of data. We should assume that the data that we are calculating the attributes on is clean and the data is correctly processed, and the image that you are using is correct. So how I define the attributes, sometimes I'm using tree-based techniques that are giving me quite good automation, and also I'm in this group of people that's saying that the random forest is maybe not the best, but always giving a good results to some point, for some point of the generalization. But therefore, for example, when I can see that I've got the artifacts on the attributes that has been calculated, so I'm taking a look on the data, and then I'm trying to do some post-stack denoising. So when I see that, for example, I've got acquisition artifacts, and therefore I'm doing some cleaning, and then I'm calculating attributes once again. But it's tricky as well. For example, once we were looking for particular structure, and on the clustering, we've got quite good representation of that structure, but on the seismic data we were seeing a lot of acquisition noise, and surprisingly, after removing that noise using a post-stack techniques, noise attenuation techniques, then the structure was less visible. So it's hard to without seeing, without going detail in each particular case, to answer on that. And this is a problem in the industry, that domain shift, and that we very often needs to retrain the model quite often, because first we've got a different geology, then we've got a different acquisition, different tools, and we've got the different processors and different interpreters, and all of this are giving us quite different statistical representation. And of course, everything is good when we've got a model that is designed for the particular statistical representation. But when the probe or the data set is changing, then we've got a problem. And here we've got a lot of variability in the data. Yeah, it's a domain problem, obviously. Of course, we are not doing like, I don't know, let's say the companies that are using our data that we are producing every day, clicking something, and we are like a social people. Yeah, we are people, so we've got some social preferences, and therefore it's easier to make more generalized models, more robust models that are not that they don't need that much of customization going from field to field. But yeah, it's what I can say. I'm using my eye, the techniques, the machine learning techniques to see the outliers. I'm trying to use also the statistical analysis, but for a 3D data set, it's not the easiest one. And what I can say that I'm always focused on the target. So when I, for example, focus on particular target in the particular depth, then I'm not focusing on the other parts in case of the outliers and so on. Or also you can use deep neural networks and check if they can deal with the good prediction with the outliers included in the feature data sets. I don't know if it's answering that question. I wouldn't be very happy with that answer, but I don't have better one.
The honest answer is always the best one. Mateusz, I will mute myself now and you just go ahead. We have 2 more questions, but we will address them in the Q&A.
I mean, yeah, or we can address them now and then move to the another part.
You good like this?
Yeah, sure.
Yeah. So Mohammed was asking us, why should one use machine learning to display and interact with seismic data rather than using, for example, softwares like Petrel?
Of course, you can use if you know how to use the software, and always better choice is decision-space geoscience. But of course, if you've got the software and you know how to use it, therefore use it, do the calculation, see the data. I was showing here the way how you can do this for the small data science project if you don't have access to that kind of the software, which is quite expensive, and if you are not in the domain, so you won't need it for every day. So this is the answer. Of course, I'm also using for all the attributes that I'm calculating for my projects, I'm using decision space geoscience attribute calculation. I'm also using our platform, which is ds365.ai, where we've got like predefined tools to deal with the data science projects.
Thank you, Mateusz. Adam, I mean, he had quite a comment and a question. I'll read it, and Mateusz, if you can answer, it's fine. If not, we
Okay.
can take this question for the later bootcamps, which will be closer to the hackathon phase. So not necessarily a question for you. Adam says, but this all sounds quite complex. Maybe just to my reservoir engineer brain. When we will get to the hackathon part, we will be given significant examples of ground truth or correct interpretations to compare with the output, or our code will be reliant on our own expertise or lack of for verifying the results.
No, so this is definitely not the question for me, but rather for you, Laura, or for the organizers, because I don't have the details how the final result will be graded, what will be the feedback at the end.
Yeah, this is that's why I knew you will not answer this, and my answer today is that this will be addressed in the later bootcamps. We have specifically one of the bootcamps, a Q&A session with the owners of the data set, and they are G&G experts who will be there to answer all these questions. But what I can promise is that Adam, we take this question, we keep it in mind, and we will make sure it will get answered in that live session or via Discord when we will get closer to the hackathon.
Okay.
And yeah, all the others. So we have 2 more comments. Adam said, okay, no problem. And yeah, indeed, you can post it on Discord. So thank you, Mateusz, and I think at this moment we are done.
I can just add that it's hard to define the ground truth in our industry. What is the ground truth at the end? Maybe if we do the modeling, then we know the ground truth, but yeah, we for sure will never know the whole subsurface with 100% accuracy. Let's maybe I will show you right now the case study that I was doing to see to show you the way through the whole process, and then I will come back to the Python again. But give me a second. I need to go to the Zoom, and I will start a new share. Please let me know if you can see the presentation.
Yes, we can see it.
Okay, so
and it's in full screen, I guess. Yeah.
Full screen, yeah, it should be full screen. I will be skipping a lot of parts which are not important, like equations and so on, but we'll give you a high-level overview how complicated can be data science in the industry, project in the industry. So this is introduction about myself, but we already done it. So my PhD was about the exploration of the practicality of walk-away VSP to specify elastic properties of geological medium. As I told you, I'm based in Poland, and in that time when I was starting my PhD, we've done a lot of studies and research for the shale gas. And it was the first walk-away VSP acquisition in Poland. And my project was about how we can use it to improve the velocity model, to improve the information about the velocity field to make the better imaging of that area. And it consists of three parts that were equally important. So first one was data processing with the classical statistical analysis. Then I was developing the software based on Greczka and Matieva papers and work done about P-wave only inversion for anisotropy parameters. So I was trying to reproduce the full tensor of anisotropy using only P-wave. And then I use the result from that part as my machine learning feature that was supporting later on the interpretation. So here you can see where we are. We are in Poland. So the acquisition was somewhere here at the northern part of Poland. Here you've got the geology. What was the problem for the 3D seismic was that part. We've got the section formation, which consists of salt and anhydrite with the very high velocity. You will see later on. And of course, this is causing the effect that we are unable to clearly see what is beneath this one. It's exactly like with any other methods that the electric current likes to have to be in a layer where can run without any problem, and with the P wave we've got the same wave where the velocity is high, then and the inversion in the layer beneath it, then the imaging is hard. And unfortunately, our target was here. And here you can see that it's quite similar lithology based, made mostly by Marl and Clayston. What is surprising that we should expect that the signal to noise ratio will be decreasing with the depth, and here we've got a different situation. So I was also investigated that phenomena why you can see this effect. So here you can see the acquisition. We've got a well, and there we've got like this sexton formation and 96 receiver. And let's move on. First, I was doing data processing, and I was doing the analysis, what kind of the statistical techniques can be used, and what type of the processing sequence for walk-away VSP study can be used to have the best representation of different angles and best representation of first breaks for P-wave. And I also designed a statistical matching filter for sweeps that were done on the same shooting point, because there was a sweeping done many times at the same point to do the vertical stacking to reduce some kind of the random noise. But we've got a little bit problem with acquisition because it was after heavy rains and there was not much time to do the acquisition, and therefore you can see how the vibro size looks like. and the near surface zone between sweeping change a lot, as you can see here. And the basic concept of the rotation, so I've got a well with the receivers in it, with the vertical component and the horizontal component. What I needed was to get the angle between the ray incident and the foul component to be able later on to calculate the P-wave inversion based on the polarization angle for the inclination. And you've got the different methods here, and the principal component was the best one because it was giving us the most energy transferred from those H1, H2 components to the vertical component. Yeah, I will skip that one as well because it's not important for the data science. Then I was doing the noise cancellation, so you can see the basic parameters for the denoising of the data set. And here you can see the example. This is the raw gather for the shot point number 34. And this is the same gather after denoising. So you can see that the denoising was quite good. And then I need to evaluate which processing techniques was the best. So I was doing the statistical analysis. I was analyzing signal to noise ratio, the inclination changes with the error of estimation of the inclination, and then I was analyzing the box plots. Here you can see that is a quite difference between the different processing options and the inclination obtained from that. Option 2, 3, and 4 gave the average value in the same places, more or less, but the option 1 was giving a totally different value that when we recalculate it to the offset, it is giving a huge difference. So therefore you can see that option 3 and 4 are quite similar, but at the end I choose option 4. I will tell you later why, but here you've got a good example why the way of how you're doing the processing. All of these 3 options were good in the theory. So this is the image that you will get at the end. It's very, it's the human error can be huge in case of processing, and I will skip going closer to that one. Here you can see the comparison for near offset and far offset, the different analysis, the different inclination angles for the receivers. So here, if you can see the receiver angles is equal to the depth. And you can see that error is going down. For me, the cutoff of the error for average inclination was 2 degrees. So you can see that here all of the options for the offset, the close offset were okay, but for the far offset, no, here I've got like a 5, then I've got 3. It's much above the cutoff. I choose option number 4 because of the distribution and of course because of the lowest average error. But when I added also the signal matching filter to the option number 4, to the processing with option number 4, you can see that I reduce the error even by half. So the statistical techniques can be very powerful. Then I was doing the kernel density estimation to see how it is distributed, and we can nicely see because there we've got the 4 major complexes, and here we can see them easily. But also I will skip the detailed information. And now you can see the swarm plots for different shot points, which is a different offset. What I mean by the offset is the offset is the distance from the well to the point that was making a wave, so for the vibroseis. And here you can see that we've got like a different groups. Here is the one group, here is another group, and here is another group. And of course, when we are going farther from the well, and then our signal, which is traveling through the subsurface, has much more things that can disrupt the signal, then we will be seeing, like this kind of the distribution. But basically, I can divide my shot points area based on the three groups, and of course, this has explanation when you can take a look on the acquisition, but I'll not go to the detail. Then another QC, another effect that I've got the trend here with the error that it's growing for the offset up to 3 kilometers, and then the error is decreasing. So this was the question also, why is decreasing like that? And I was checking that many times because it was much I was not expecting that, to be honest, and it was hard to explain that, but of course explanation cannot be done on only 4 points. So hopefully when they will doing the acquisition again, I will have the answer for that. Then I was doing the P-wave only inversion to make the local anisotropy estimation. What is the anisotropy? It's when we are doing the measurements in a different direction, then we will have a different physical parameters value. Here it's related to the velocity. So for example, if I will be putting something like a source here and receiver here, I will have like a higher velocity, and when I will put the source here and the receiver here, I will have, for example, lower. So depending on the direction, I will have a different values of the physical parameters. So here is here are the equation, and now you can see the predicted value based on the code created from the equation that I show you for the points that were taken to do the inversion. And here you can see the outliers that were specified here. And here you can see how it will be looking where the subsurface will be isotropic. So where we will have the situation where it doesn't matter from which direction we are doing the measurement, the velocity all the time will be the same, because this also can be a case. And when we are going to the different depths, which is equal to the different layers, we can see that, for example, here we are in a perfectly isotropic layer. And then here you can see the anisotropy parameters and elastic properties calculated from that code and calculated from the well log. And here you can see average of those parameters calculated in the main complexes based on the core analysis. And now machine learning part. So I've got my VSP data. So VSP data are the data where the receivers for the seismic observation are in the well, and the source is on the surface. And the source is behaving exactly like in the 2D data set or in the 3D data acquisition, but the receivers are all the time in the well. And I've got 31 different inclination that I calculate. I've got the anisotropy parameters from the inversion, and also I've got velocity not from the inversion, but directly from the first arrivals. And then I've got log data in different units and parameters calculated from log data. But you can see that the values for the parameters were the range of the values were quite different. So some kind of the techniques that will allow to compare them to each other, especially that I was doing some kind of I will show the clustering example. So then the values, the range really matters, yeah, because when we will have the values, for example, those will be dominating the solution if we don't do anything. But there was also another problem about the resolution, because in case of the well data, I've got the resolution 15 meters. For well data, I've got resolution for 10 centimeters. And when you will be doing this hackathon, probably you will have also well data and you will have a seismic, and you have to remember that those are in different resolution. So this is also some part that you have to remember about. And here I put the example of the resolution and the range. So you can see that we can have very high resolution using ultrasonic measurements, but the range of that we will be able to see in case of the rock will be very limited. And when we are going with the seismic methods from the well and then going to the cross well to the VSP, 3D and 2D seismic, then we can get the lower resolution, but the range of observation will be higher. And now the question is, what is better? And it's not easy to say. All of them are needed, and we have to take a look on the subsurface from different perspectives, and then to find the way how to deal with those different perspectives in our machine learning algorithms. And here I've got two scenarios. Scenarios one, it was upscaling well logs to the VSP resolution. Scenario two was downscaling the VSP measurements to well log resolution. And what is the outcome? In the first scenario, I will filter out minor variation and I will leave only the main lithological changes. So I won't be able to see the sophisticated detailed changes in the subsurface. I need to do some kind of the smoothing filters or Backus averaging, blocking intervals. There is no good techniques to do this upscaling, to be honest, and all of them has a pluses and all of them has a kind of disadvantages. But I will say that we will have a data set very compacted, which will be easier for me to do the test. I will have noise reduced that were in the well logs through that generalization, but it's a not trivial task. And in scenario two, it's easier because I will just produce more data. So I don't have this interpretation step. So I don't need to decide what to delete from the data. Because obviously I will here reduce the noise, but I don't know if I will, probably I will also reduce the signal, yeah? In that scenario, I won't reduce the signal, but of course, I will produce much more data to get the same resolution, but no new information will be obtained after, let's say, the simple interpolation, yeah? Because it's enough to not give additional error just to have the similar resolution. And you can see here a comparison of the data points. And then I was doing the clustering and I was checking different validation techniques from this typical one that you will find everywhere up to the interpretation, which of course is needed in case of the algorithms where you need to specify a priori the optimal number of clusters. And of course, I was using big criterion, which is the most favorite of my advisor in that advisor of that PhD. I was also using additional features that I've got from microseismic observation. Here you can see the microseismic polarization analysis and ellipticity changes from that way of looking on the subsurface. And here you can see the resolution for the VSP, and here you can see the lithology for sonic. And what when I'm going to 8 number of clusters, I can see here that something was found in a Gaussian mixture and Cummins. This is very important because we know from the previous observation that here we've got a saturation. So it was good to take a look to find that way of clustering the data set that will be able to see those changes. And you can take a look how it is changing. And you can see, of course, how those are similar to each other, which we can expect, and how the spectral clustering is different, but not necessarily worse. Yeah, it's giving a different perspective, and this is a great in data science that we can use like different algorithms for the same purpose, but they also can give us a different perspective, and also later on it can be used as a feature. And here you have an example of a different resolution. When we will increasing the number of clusters, then I'm able to see also other important part of that claystone that I was looking for, but then I'm not seeing here the difference. But as you can see here, I've got like a claystone and Merli claystone. Then I've got this division on Merli claystone based on the saturation. But oh yeah, in case of the geology, I'm not geologist, but of course it can be more similar to this, even with saturation, than to those two, the claystone itself. So those was what I was doing in my PhD as a project for this complete study, I would say, of the subsurface, using many observations of the same effect, because I was, as you can see here, all the time using the elastic measurement. So I was using VSP, walk away, and P wave recorded. I was using well logging and acoustic logging, so it's again elastic field. And then I was using microseismic as well, which is also using the same phenomena. And therefore you can see how we can use all of this to get the results. I can tell you that 8 and 12 was chosen for a different purpose as the best one here. So any question for this?
Mateusz, we do not have anything in the chat
Okay.
at this moment in time.
And so now I will. How much time we have more left?
So it's so we had so far 1 hour and 20 minutes, and now it's on you. How long you think you still need? So
okay, I will try to show the last one. It will be again related to the clustering, because I didn't want to show you the techniques that can be used exactly into this hackathon. Yeah, to not give you any like a pre-assumptions, or to not program your minds.
So we can still cover easily 20 minutes.
Okay. So yeah, I will go back to the Jupyter notebook.
Yep, we
so
see.
I hope you can see it. So here I'm using Evolve dataset. Probably those who are from the industry or were in the other hackathons related to the GNG data and to oil and gas industry probably know already the Evolve dataset, which is in North Sea and was operated by Equinor. So here I will be using publicly available data again, and I will be using different different logs. First is neuron porosity, which can help us to get the information about different things, but mostly about the amount of fluids. And of course, when we are in GEG, we are focused on hydrocarbons. Then bulk density, where we can get the weight and the density of rock formation per unit volume. Then the gamma ray, which is our reference measurement and also can help us with identification of certain types of rock formation, and can help us to estimate the amount of organic matter in the formation. Resistivity log, which are done for different separation between the electrodes, and then we are able to determine the presence and quality of fluids within the rock formation. And also we can get information about water oil contacts and things like that. Then photoelectric factor logs, where we can again use it for different purposes, but mostly for estimation of sandstone and presence of organic organic matter in the deformation. The caliper, which is useful again when we're doing the interpretation to see if, for example, we've got different type of rocks based on the higher or lower caliper together with the, for example, acoustic logs. But I was talking a lot about the acoustic logs, so delay time here, travel time here you can see, and it is used mostly to determine the rock formation's mechanical properties and porosity and permeability, which are pretty important for reservoir engineer. Yeah, so here's a reservoir engineer. So those parameters like porosity and permeability are pretty crucial. And of course, if we've got the P wave travel time, we can also have like a shear wave travel time. We are calling this delay times. And when we've got S wave, of course, it's hard to measure to get the information about S wave from the well when we've got the fluids, but we can assume that in certain range of the frequency, the flexural wave has the same velocity as shear wave. And therefore, of course, when we've got this P and shear wave, we can calculate the anisotropy parameters, for example, which are indeed mechanical properties and elastic properties of the subsurface. So first, I prepared for myself the combined Excel file with those measurements, and here you can see the different measurements that are in different ranges again, but we need to plot it, and here I plotted using this code. Of course, I told the colors are important, and for me those colors are nice. So and we can see those logs in the depth domain, because logs are measured in the depth because we are drilling the well. We know the depth, and the problem with seismic is that we are measuring the seismic in time, and we need a good velocity model to translate the time to depth. And you can see that something bad is happening with resistivity log, or it's something wrong, or this is the outlier, and we can check it. Of course, we notice something strange with RT curve. And now when we do the box plots, so we can see that in each of the log, we've got some portion of outlier. Sometimes you got the different skewness of the distribution, but the RT is having a very, very big outliers. So probably we can say that it was related to the measurement system, or something that was causing up normal values of the resistivity. And it can happen, yeah. Of course, when you add where you are doing also the resistivity observation on the surface, sometimes you can also get like those kind of values, and it's quite typical. So first, I can do very basic outlier removal. So let's start from the most easiest one. So I can see that those are for sure the outliers. I will remove all of them and replace all higher than 100, yeah, because here I've got 0, let's say, and replace with the non-values, and then I will interpolate the values from the nearest one. And we can see that it is looking like that after the simple outlier removal. So those measurement related outliers can be removed simply by this filtering of data that are abnormal to the range of the measurement that we are expecting. And here RT curve is looking correctly and normal. And then let's plot again the box plots once we remove these big outliers. So we can see that, okay, we remove those outliers, but there are still many to be deleted probably, or maybe they are not outliers. So for that, we have to use different techniques. Here I show you also that we can use a seaborn. In general, I'm using a seaborn for the visualization, the library, but sometimes, for example, the box plot like that, or the well logs, I'm using the typical matplotlib. Once I create a nice function, then I'm using it for the visualization of everything. And I like to visualize, to make the visualization of the data in each point. So I know that there are people that are not doing that much of visualization, and they are referring to the metrics, which is also a good one. But for me, EDA, it's something that is crucial. And when we are going to the EDA, so for me, it's the one of the most important part of the whole workflow. I don't feel comfortable when I'm not doing the EDA because I don't know the data. And I would like to know the data. I would like to know the distributions, and I can capture better what's going on when I'm seeing the distribution. I don't know if you are using all the time for the plotting of the histograms the same and default values that are when you are plotting the histogram, but I strongly advise you to use the Friedman-Diaconis rule for determining the optimal bin numbers for the statistical analysis if the probe is big enough. Once I found that rule, I found it very useful to get the correct visualization of the histogram to capture what's going on. And here you can see when I calculated the histogram based on this rule that I can see this very minor changes, but also I can see the whole distribution. And here you've got all of the measurements in the one line, but if it will be like having a little bigger size, it will be even better visible. So I advise you to take a look on that rule when you are doing your histograms. Then, of course, some kind of the typical techniques like a payprots to see the distribution. Here are the raw data without any previous techniques applied for the measurements, standardization or something like that. Then another technique that you can use is a correlation matrix to get the Pearson correlation coefficient between different features. So yeah, we can see that we've got here and here quite high correlation. Maybe we can reduce the number of features for the analysis, but for that it's always good to do the PCA and to check that. Now the step 3 after this, let's say, raw data, EDA, it's a data normalization. And again, here I will be doing the clustering again. So this unsupervised kind of the machine learning, and the data normalization for Cummins is important. And I also will transfer resistivity logs to logarithmical scale, because this is a typical way of analyzing those kind of data, and I won't go too much into the detail why, but in general, the resistivity logs we are looking on with the logarithmical scale. Then we can check the distribution of the data, what kind of the distribution there is. Of course, the best one will be that one all the time, but the life is different. We've got different distributions, different signal included in the data, so we need to therefore a different way of looking on the data. And again, the payprod now on the data after normalizations, this is the better way to look on that kind of the summarize, let's say, visualization of the statistical features after the normalizations. But I always doing it before and after, and then I'm doing a comparison. And here again, after the normalization, we can see what is the difference between the distribution on the box plots, which is very useful, especially when we've got that amount of observation. Now we can go to the another step of outlier removal. Here I will be using the isolation forest. The concept probably is well known for everyone. So let's jump to see the results. Still, we've got some outliers. We can do it better, but just to see the first facious analysis based on the on this data, we can proceed. And I was using here Cummins algorithm for a clustering of this data to see the facious based on those observations. And here you can see the results, and you can see also the similar to the one that I was using for this elastic parameters. But it's not enough. Here I put 10 because I put 10. But of course, there is a need to, okay, sorry, I didn't run that code. But then you need to calculate the different metrics for seeing the optimal cluster numbers. And if you are interested where how you can calculate the optimal number of clusters, you can always, I will put a link to my paper about this cluster number estimation in the chat later on, so you can read in details what I shown you today. And I hope that at least the concept of data science, the basic of machine learning, and the basic of the data set that you will be using, with the general view of the whole process from the designing up to the interpretation, is a little bit clearer for you. If not, I'm sorry.
Thank you very much, Mateusz, and do not say that for sure. There are more questions to come, and I'm sure that more our participants will dive into this world. More questions that will emerge. Please drop your questions in the chat box. Let me see. By the way, congratulations for everything you've done with the PhD. There is a question if your thesis is public and if our participants can find it online.
Yes,
It's
my
public
thesis.
for sure because it's a PhD thesis, but most probably somewhere in Poland, I guess.
Yeah, unfortunately, the whole PhD is written in Polish, as this was the requirement from the data provider, which is a Polish company. But
Okay.
I make a series of papers that are really my PhD, and those are in English. So I can share the links to the papers in the chronological manner. Then reading the papers, you will have a PhD with the less pages than the PhD itself. So
okay, thank you so much. By the way, if we end the session and you do not have the time to also share the links with the libraries you were talking about before, maybe we kindly ask you to drop us an email and we will make sure we share everything with our participants on the Discord channel.
Maybe this will be the best way, that I will send an email to you with a nice
and
summary, and then you will reproduce
we
on.
share everything with our participants on the Discord channel, because this chat is not available after we end the session. Thank you both. So again, another question: if we can share the links for the data for the Jupyter, and if the Jupyter notebooks will be available. So you will decide what you will share.
For sure. The one I will share. The second one probably yes. I need to do some kind of the modification, and then I will share. What I can say, if you will have any questions, you can always drop me an email, Mateusz.Zareba as my name and surname, Halliburton.com, or you can find me on LinkedIn as well. I will try to help. Not much of those are on a GitHub because what we are doing is not available there. So you won't see much code that is publicly available. But of course, we can always talk about different ideas. I'm happy to.
We do not have other questions. So while we chatted here, nothing else came in the chat box. Lots of thank you. Very interesting presentation and the extraordinary work you've done with your PhD. Congratulations also from one who is not into the realm. So very interesting and sounds extraordinary. You've done it, so it's possible, but very interesting. Thank you so much.
Thank you.
I think at this moment in time we can say that we are at the end of our fourth session, and if you allow me, I will share my screen to shortly mention our session for tomorrow.
Sure, no problem.
We are going to have the next session tomorrow afternoon, same time, and we will have Luca Fava from OMV Petrom, who is going to talk about seismic data interpretation. So 11 of October, Wednesday, same hour as today, 3 p.m. GMT +1, which is the UK time. So 4 p.m. For the ones in Central Europe, 5 p.m. for the ones in the Eastern Europe. And of course, you do the calculations for the rest of the world. And Luca will cover seismic interpretation and general concept of it, interpretation itself, seismic attributes, seismic interpretation for geothermal, and some machine learning related to seismic interpretation. And with that, thank you very much for being with us today. Thank you again, Mateusz, for your time. And we keep in touch.